it's a genius. It's genius to understand that, you know, what's the smallest thing? Well, maybe a grain of sand is the smallest thing. Well, what if I cut that in half, and then cut that in half again, and then cut that in half again, and then so there was the Greeks did this, right? That I can't remember the name of the Greeks, but something like Democritus or something like that. They did this, and the word atom comes from the definition of the thing that you can't split, right? So for thousands of years, right, word atom, you can't split it. And then Oppenheimer comes along, goes, yes, you can. Let's go split an atom. And then off we go into the Cold War. First we end the Second World War, and then off you go into the Cold War. And so, you can go from the very, very large understanding from general relativity, from the genius of Einstein, to actually a whole group of people who really flipped on its head the understanding of the very small. So Heisenberg, Dirac, I'm forgetting. You know, I like the large stuff.
No, that probably you're ringing these names and bells of a project past, you know. But no, definitely,
So the uncertainty principle, Enrico Fermi, right? Okay. All of these names, they start to really unravel our understanding of the very small. And then, that's why it's so important to do these high energy experiments, right? Mm-hmm. It's because first of all, if you want to understand the very origins of the universe, we can't do that with astronomy directly, because the cosmic microwave background prevents any photons from moving through the universe, right? So the cosmic microwave background is the point at which the universe had cooled down enough for the mean free path of photons to actually exceed the size of the universe. So that means that photons can travel through the universe, right? Before that, the universe was so small and hot that the photon would just be scattered around inside the universe. And so as it expands, the photons can now travel through the universe. So it means that when you've got a telescope and you're pointing it at the cosmic microwave background, you can't actually get any signal beyond that. There's a barrier to that. Now you might be able to look at that in terms of gravitational waves, but the other thing that you can do is you can say, instead of trying to see that, why don't we try and reproduce it in the lab? Why don't we get the amount of energy per unit volume that the universe had at that time and see what physics comes out of it? And that's why you need particle accelerators, right? So particle accelerators reproduce the physics of the early universe. And so particle accelerators are telling us about the really, really early times in the universe and how the universe evolved then. And then once you get to the cosmic microwave background, that's where the particle physicists typically end. They think that's cold. Right? 3,000 Kelvin, they think that's cold. And then the astronomers take over and the astrophysicists take over, and they say, right, now the universe has cooled down so that we can form stars and galaxies and planets. We'll take over.